right, so we were talking about inductors last time, and inductors are interesting. So this is just a quick derivation of just like we did capacitors, right? How do they act in series? How do they act in parallel, right? So let's look at inductors. Well, let's go back for a minute. Current voltage relationship. Let's see, inductance. Remember, in an inductor, right? The current is what changes with time, right? Well, I mean, obviously the voltage drop over the inductor changes with time, right? But the current is a function of voltage is a function of time. So if you have a constant voltage, at some point you reach a constant current. That's what we discussed. And let's look at this from the standpoint of voltage drop. So we have this circuit, right? It's got 1, 2, 3, n inductors in series, right? So at some point, you're going to have you're going to have a voltage drop over each one of these inductors, right? And at some point, the current is going to sort of become, equal. But if we just look at the KVL combination, right, we know that we can we have V equals the sum of the voltages, right? So you can get an equivalent inductor by doing what to these things? Well, let's see. Well, let's see. The sum of the voltages is just going to be inductor number 1, di dt, right? So how are the currents changing through this inductor? You've got, the inductance 2 times that di dt, right, et cetera, et cetera. So basically what you can see is you can factor out di dt, right, is going to be the same, right? You can factor this out, because if the current is changing, well, this is just the same di dt, right, throughout. You can factor this out and just it's the sum of the inductances, right? So basically the equivalent inductance is just the sum of all the series inductance. So inductors behave the same way as resistors. And that means they're going to behave the same way in parallel, but let's go through that so we can see what's going on. Remember, with all these inductors now, you have the same, voltage potential over the top, and you have the current is going to be based on the inductance now, right? So you have, let's see, current is I1, the sum of the currents, right? This is just Kirchhoff's current law. The sum of the currents at this node is the sum of the currents at this node, right? Sum of the currents is just I1 plus I2 plus I3 plus all the way to IN. Let's look at the current voltage relationship, right? In the case of an inductor, we've got the integral from whatever time to some other time of V dt, right? Plus some other constant. And notice, right, the sum, or this is the sum of 1 over the inductances, right? So each individual inductor is 1 over L. So like say 1 over L1, the integral V dt, right? And what's the voltage drop? Well, the voltage drop is, again, the same thing from one node to the other, right? Voltage is just a potential to drive charge, right? So you wind up with your equivalent inductance is just the sum of 1 over the equivalent inductance is a sum of 1 over each individual inductance, just like a resistor. And this constant term out here is basically just adds up to whatever the constant, whatever the total inductance is. So this is just inductance in parallel, right? Same as resistors. So inductors are, in terms of series and parallel, how you treat them the same as resistors. Capacitors are treated inverse of resistors, right? So series capacitors you take the inverse, right? Parallel capacitors, you add them. Series inductors, you just add them. Parallel inductors, you take the inverses. So inductors and resistors share that similarity. Capacitors are inverse to both of them. Let's see. Oh, this is just mentioning that you can also take the delta Y transformation and you can apply it to either inductors or capacitors as long as all the elements are the same type. So as long as you have like all capacitors or all inductors, that's what you want to, be sure you're, if you find it, you see something that looks like a delta Y and you're like, oh yeah, it's a delta Y, but it's got a mixture of these things. Don't try to break it down. It's not going to work. All right, let's do some practice problems. I thought I had. What happened to 610? Hold on. Oh my God, 610 is back here. Oh. I never did 610. Well, let's do 610 first. This is going back a little bit to just the regular, the previous calculations. Energy stored. All right, so now we got a mixed circuit here. We got a 10 amp current source. We've got an inductor. We've got two resistors in parallel, and we've got a capacitor here. So it wants us to determine the voltage VC, so the voltage drop over the capacitor, or the potential difference over the capacitor, right? Current IL, so the current through this inductor, and then the energy stored in both the capacitor and the inductor under DC conditions. So let's let's draw this out. Yeah. So I'm going to redraw this circuit because we're under DC conditions, right? With DC conditions, I'm going to replace the inductor or inductors with shorts and capacitors with opens. Now I've only got obviously one of each here, but I'm going to redraw this circuit so you can see it. And remember, this is because you don't have any information about time here, right? We don't know what's going on with time. Like we're not asked, initially, an inductor or the circuit stores no energy, right? And a current source is hooked up at time equals 0. What's the energy at such and such a time, right? We're not there yet. This is just all steady state stuff. So this is the current's been hooked up. It's been hooked up for a while. It's a DC. Well, it's a DC circuit. So what's going on? So I'm going to draw this circuit. This is 6 ohms. What I'm going to do here is I'm going to put a wire with 2 dots, and this represents where the 6 Henry inductor is. Because remember, the inductor is a short. Why do you call him short? My brother used to call me short. Well, he still does. He's 6'3", so. Let's see, B sub C. I just had a funny thought about him. All right, so this is what we have. I've replaced the inductor with a short, and I've replaced the capacitor with an open, because after a long time, right, what happens with the inductor? You wind up with initially your current goes through, and you start generating this magnetic field, right? It's sort of, oh, you know, if you watch any of the videos, they use a water wheel as an example for the inductor. So think about if you, if you had a pipe with a water wheel, right? The current is like the flow of water, and the current passes through. Initially, the water wheel is not moving, right? So your current is slowed a bit by the fact that it's got to push against this water wheel, even though you have a back pressure, right? And then after some time, you get this water wheel spinning, and it starts spinning at the same rate as the flow rate of water, right? So now the water wheel is basically, that's stored energy, right? But what happens to the water here? Well, the water is just passing through as if there's no resistance. Well, no resistance besides whatever the friction of the pipe is. So the water wheel is spinning and spinning, and that's why once you shut off the flow, right, the water wheel continues to spin and spins down, but it's pushing the water through. So that's your rise and fall in current with an inductor. Capacitor is kind of like a charging up a tank. You've got these two parallel plates, and you've got a current that generates a voltage difference, right? Voltage drop between these two nodes. And because there's a voltage drop, right, initially you get current flow. Well, you get current flow in the sense that you've got positive charge, and then you've got positive charge flowing away from this end until the potential, or the potential difference over the capacitor is such that you don't have enough voltage to drive any more difference in charge. Right, so the capacitor is charging up. It's kind of like a charged, it's sitting there, a charged tank. It's full, right? So you're not filling it up anymore. All right, what was this? Oh yeah, so the point here is this is 10 amps, 6 ohms, 2 henries, DC. Oh, this is 4 farads. I'll put a 4F over here. All right, so initially the current, or not initially, but once this circuit's been turned on and has reached some kind of a steady state, right, the current splits between, it looks like, well, let's just look at this, right? The current can pass through here, but it can't pass through here because it's now a short. The current's got to pass between these two resistors, right? Between the 6 and 2 ohm resistors. So we can just use current division. I'll just make a note, use current division. So IL. Oh, let me draw this out here. Red pen, there it is. IL is going to be the split, right? IL is the current that's going to be going through the 2 ohm resistor, not the 6 ohm resistor. So we know for resistors in parallel, the higher this resistance is, right, the more current goes through there. So we take the higher resistance over the total resistance. So we've got 6 over 6 plus 2 times 10 amps. And here you get 7.5 amps. That's IL. Now, we're trying to figure out what's the voltage. Well, the voltage is going to be the same thing. Let's write this out. VC, right? VC is just the same potential difference between here and here, right? Let's just do this, the ground. This voltage drop is just this voltage drop. So So we've got V1 minus 0 over 2 ohms, right? Well, V1 is just IR. Let me just draw this here. V1 over 2 ohms. This is the current IL. I don't know why I said well, IR being. This is the current through that resistor, right? So V1 is just VC. So this means that VC equals 2 ohms times 7.5 amps. So VC is equal to 15 volts. So those are our two, these are supposed to be subscripts. That's our voltage and our current through the inductor and over the capacitor, right? Again, using the concept that voltage potential difference between these 2 points is the same regardless of it's over the resistor or over the capacitor. They both join at the same node. So this is something that I think maybe throws people when we start mixing things or mixing the components, right? I mean, to this point, you've always seen it with resistors, right? Resistors in parallel, resistors in series. The same concepts still apply, particularly voltage potential, right? You still have this node up here, and you have this other node over here, which, you know, I arbitrarily chose as ground. You've got this voltage potential over it, right? And that's the same as this voltage potential over, you know, it's between here and here. If this was you know, this potential is governed by the fact that you've got these components, you know, sitting there, and you know, regardless of what the resistor is, you've got to have that difference, and the capacitor is going to build up that charge, and it's going to stop the voltage. So you know, the potential on this side has to be higher than the potential on this side, and that's just the highest it can be is the potential difference over this resistor, right? Like if you increase this resistor, you could develop a higher potential, right? And you could build up more charge in the capacitor. So if that's something you wanted to do, right? Now, obviously you'd have this thing to worry about, but in terms of the voltage potential, your charge, your total charge, you can control how much charge builds up on this capacitor by how much of a resistor you have there. Okay, so we're not done with this problem yet. We want to find the energy stored in the capacitor and the inductor. So let's do the work, or the energy for the capacitor is 1/2 CV squared, capacitance times voltage squared. Here we've got 1/2. We've got a 4 farad capacitor. We've got a voltage drop of 15 volts. So let's just put farads and volts. And this equals 450 joules. This is the energy stored by the capacitor in capacitor. All right, let's look at the energy stored in the inductor. So now we've got 1/2 inductance times I squared. And what were we given? We're given 6 henries for the inductance. I might as well write the units in. And the current, right, 7.5 amps squared. And this gives me 168.75. I mean, you can round up to 169. I just want to show you the joules. Oh, I don't know why I wrote that out. This is the inductor. That seems a little odd. Inductor. Inductor. So that shows you how much energy they each store. Right, and that's energy that can be given back to the circuit, depending on how you're using the circuit, right? If you you know, this is just a generic circuit for you to problem solve with. But in reality, right, inductors and capacitors are used to, you know, to do things in the circuit, like, you know, dampen out fluctuations, or, you know, power things up, or, you know, kickstart things like capacitors kickstart motors. All right, let's go back to the. All right, so now we went through. Oh, okay, so here we are. We're at the problems that I thought we would be at today. I don't know why I noticed 610 was not. This one is very straightforward. This is just looking at inductors in series and inductors in parallel. This is this first one here, right? Equivalent inductance for the inductive ladder network. This is going to be really straightforward. So I'm going to kind of go through it pretty quick. Let's see. These 40, the 40 and the 20 are in series. I'm going to start from the outside and go in, right? Just the same thing you do for a resistor network, right? In here, you're like, I have no idea where to start, right? You start with the outside here, where you can start lumping things together. And you can see this is basically, you know, 60 millihenry, oh, 60 millihenries. And this is in parallel with the 30. So I'll just put a note here, the 40 and the 20 in parallel with the 30. And this gives me, let's say I've got 60 times 30 over 60 plus 30, right? This is just the same equation we use for resistors in parallel, except this is inductors now. So here we wind up with 20 millihenries. That's this whole thing here, right? So I'm going to redraw the circuit. I'll draw it like this. Inductors are a little easier to draw because you get this whole curly Q thing going. It's kind of fun. Curly, 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 curly. All right. Let's see. I need a few more. I got the 100. And this is the one I just came up with. So here we've got 20, 40, 100, 50. This is all millihenries. And over here, I'm going to write the 20. From there. That's my new circuit. So now I've got 120. The 120 in parallel with the 40. Right, so I've got 120 times 40 over, we just add them up in our heads, right, 160. And this gives us 30 millihenry. So again, just going through the same steps you would for a resistor network. Not too complicated. So here we've got 20, 50, and this is our 30. So now we've got 20 and 30. I mean, when I say 20 and 30, I'm talking, these are in series, right? You can sort of figure that out. They're in series. I'll write that, right? In series. Both in parallel with 50. Right, so here we've got 50. Oh, we got 50 and 50. So we got 50, 50 over 100. Here you wind up with 25 millihenries. And I think by now you figured out if you have equal resistors, you just, they split, and equal conductors, right? Or equal inductors, they split as well. So the 50-50 cuts in half. So the equivalent inductance is 25 millihenries. Again, fairly straightforward, just like resistors. Well, maybe resistors weren't straightforward, but now they are because you practice so much. And the inductors are by default now, because you've mastered resistors in series and parallel, inductors are, just as easy now. Let's see. All right. The next one requires some analysis. For the circuit to the right. All right, now we're given some transients here. So we've got to go back and use our knowledge of how these things change with time. And this is all inductors. So nothing crazy yet. Let's see. And we're given a function. Let me see if the function's the same. Oh yeah, this should be an e to the minus 2t, not 3 to the e minus 2t. So it's e. E is the the natural log. Well, obviously not the natural log. It's the inverse of the natural log. It's e, 3e to the minus 2t. I've got to correct this. And it tells you if I naught, right? So the initial current is 7 amps. And this is what you're given, right? This is look at the difference here. I is 7 amps initially. And I1 is 3 e to the minus 2t, right? Find I2 at 0. So we're going to find I2 at 0. And then we're going to find I2 and IT is a function of, well, I2 and I is a function of time. So we're going to find generic functions for those. And then we're going to find the voltages, V1 and V2, and the total voltage VT as a function of time. Now notice again, right, looking at this, circuit, you shouldn't have to be given this, right? You should recognize, oh yeah, the voltage drop over these two things, right, is the same. You can't have a higher potential over one than the other. Because it's going to even out, right? Whatever one's the limiting one is going to result in increasing the potential here. So you've got this potential drop, and then you've got this potential drop here, V2. All right, so let's look at this thing and figure it out. All right. The first thing I want to do is I want to look at time equals 0, right? So when you're looking at this time equals 0, you're again looking at an instantaneous shot of this this system, right? And what we're told is I naught is 7 amps. So start with A. At t equals 0, right? The first thing we can write is we know that I equals I1 plus I2, right? That has to be the case. The currents have to split up, and we don't know the ratio yet, right? However, we're given, what are we given? Oh, we're given I1. Given equation. Oh, we're actually given, oh yeah, equation for I1. So I'm going to rearrange this. I2 equals I1, or sorry, I minus I1, right? We know what I is. So let's write this out. We've got I of 0 minus I1 of 0. So I'm going to plug in some information here. I've got I of 0 is 7 amps. I1 of 0 is this minus 3e to the minus 2 times 0, right, amps. Now I wrote it out, obviously e to the 0 is 1, right? So this is just 3 amps. So you wind up with I2 equals 7 minus 3, right? So from here we see I2 at time 0 is 4 amps. Right, so this is just a simple KCL analysis, right? The only thing here is recognizing this is at that instant, time equals 0. All right, now we want to find I2 as a function of time and I as a function of time. The first thing we need to recognize is that the voltage drop over these two inductors is the same, right? So V1 is, I'm going to write this in terms of inductor number 1 here, L1 di1 dt, right? And what is that? We have a function for I1 as a function of time. So I've got 6 Henries times the derivative with respect to time of 3 e to the minus 2t. I need to put another. So let's see, this is just going to give us V1 equals, we're going to have 6 times, we're going to have a negative 6, right, e to the minus 2t. So we've got minus 36 e to the minus 2t. That's our voltage. So now we have voltage V1. So now use V1 of t to find I2 of t. So now we can look at di2. Maybe I should have backed up a little bit. I'm just taking this equation for for I2, right? I'm going to have V2. I'll just write it out. You know what I'm going to do here? Well, I'll just write out the equation for. However, this equals V1, right? Because V2 equals V1. So now I've got this equation here. I'll just put some dashed lines around it. And I can integrate to find I2, right? So from here, I'm going to wind up with di2 equals, let's see if I can put I've got 1 over L2 integral, well, it's still di, v1 dt. I'm going to integrate both sides now. Yeah, I should have put the integral there, I guess. So let's do from 0 to t. Move this up. di2, we're trying to solve this, right? Equals that. So let's take each component from 0 to t. We've got 1 over, what's L2? L2 is 3 henries. Now it's a constant, I can pull it out. I'm just trying to lump it. I actually ran out of room here, so I forgot to put it in. V1. V1 is the minus 36 e to the minus 2t. Don't forget to add on your integration constant. This is 4 amps, right? We were given this up above. Well, we're given it in terms of we solved for it, right? We solve for that. Oh, this is I2, right? This is the generic. Well, this is the generic equation. We've got to add, obviously. Once I put the integral in, then you got to add the integration constant. But I guess this should technically be I2, right? Let's lump this together. Let's reduce this thing. So we've got, we're going to have a minus 36 over 3 out here. So we're going to have minus 12 integral 0 to t e minus 2t dt plus 4 amps, right? And this is going to give us, when we integrate this, right, we're going to get a minus 12 over minus 2 e to the minus 2t from 0 to t plus 4. So this is obviously just 6. In this case, we've got 6 e to the minus 2t minus 6 e to the 0, right? 6 e to the minus 2t, and then plus 4. You know, the history. So what do we got? We've got I2 of t equals, we're going to have a minus 6 plus, well, let's write this first out front. 6 e to the minus 2t minus 6 plus 4 gives us a minus 2. I'm going to put this in parentheses and put the amps out there. I don't like to. So this is I2. This is the formula for I2. Notice we didn't do anything new here. All we did was use a current balance at the node to figure out what the relationship between the two currents are initially, right? And then we said, with time, we know the relationship between voltage and you know, the change in current with time. We have a function for the current, right? We can find the function for the voltage, V1. And then we can find the, we know V1. Oh, this is a poor, all right. This is not, Jesus. All right, this is not, this V2 is not this V2. This V2 is over the other. Someone's really got to work on these diagrams, Broad Hill. This V2 is over the 3 Henry, right? That's the I2 V2. Oh, man. I might have to go in and relabel this. Let's see. So, oh, this is I2. And then now for I, right, is just I1T plus I2T, right? So I of T is going to be this plus the initial function we were given for I of T up here, I1 of T. All right, so we're going to add 3e to the minus 2t plus this. We're going to have 9e You know what? I'm just going to write this in down here. That's what this function is, right? So I'm going to get 9 e to the minus 2t minus 2 amps. So this is part B, where we're trying to figure out the currents. Any questions about this one so far? All right, so now what we're going to do is we're going to find, which probably should have been labeled V3. We're going to find V1, V2, and VT. So we're going to find these V1 and this V1 and this V2. I should not have used V2 here. I should have just called it the voltage through the current through the 3 Henry. Anyway, just so we're clear, right? This V2 is not the V2 through the 8 Henry inductor, right? This V2 here is in the context of this current split, right? 1 and 2. I was just saying that the voltages are the same, right? So the voltage through, this is through the, let me just write this down. Over 3 Henry inductor. All right, just to differentiate, it's obviously the same as V1. All right. So now we have the circuit, and we know the functions with respect to time. And in fact, we've actually solved some of these. V1 is a function of t. Let me stick this underneath so we know what we're doing. V1 is a function of t is just equal to negative 36 e to the minus 2t. This we got from, found in part B. Remember in part B where we actually did the analysis to try to figure out what V1 was. We found V1 as a function of time, so we found that one. Now, let's look at V2 as a function of t. This is going to be equal to L di dt. Now, this is the total current, right? It's not current 1 or current 2. I splits into current 1 and 2, and then it goes back to I over here, right? So this is, again, I. So that I goes through this inductor, and we have a function for I, right? So V2 of t is going to be L, which is 8 Henries, d dt. Now, what's my function? My function we found over here, 9 e to the minus 2t minus 2. So 9 e to the minus 2t minus 2. All right, we're just taking the derivative with respect to time. So here we wind up with, let's just do the math here. We've got 8 times negative, well, I'll bring down the negative 2. I'll write it all out. Times the 9 e to the minus 2t, right? Obviously, the derivative of 2 with respect to time is 0, it goes away. So V2 with respect, or as a function of time, is equal to negative 144 e to the minus 2t. So we got V1, we've got V2. We need to find the total voltage, right? Now the total voltage, we got a voltage drop here and a voltage drop here. So the total voltage is just the sum of the individual voltage drops, right? V1, oops, 1 of T plus V2 of T. So what do we got? Negative 36 e to the minus 2t plus negative 144 e to the minus 2t v of t equals negative 180 e to the minus 2t. So this is our final voltage as well. So again, fairly straightforward from the standpoint of a circuit analysis point of view, you know, if those were just resistors. But now we've added, and inductors, this would be really boring if this was DC, right? It would just be, I mean, you wouldn't have anything going on here. These are all shorts, right? In a DC circuit. But what we're given is we're given some function of time, right? So now we're throwing in this function of time. So now you got to use your calculus. And yeah, that's, are there any questions about this one? I think, let's see, what time is it? 10:20. All right. So let me just do a quick poll here. Oh, you know what? Before I do that, let me pause for a minute. Since since there was a low turnout in the beginning of class, I thought I'd wait and just remind you all two things, two announcements. Remember, I sent out the STEM scholarship. Is this gonna? Yeah, I sent out this email to you all back on March 10th. So if you didn't get it, email me, let me know. But these are two scholarships for STEM. I meant to talk about it last week, but I didn't. Or well, yeah, I sent it out March 10th. Let's see, Patrick Lee Foundation Scholarship. This is the one that's sort of generic. Let's open this. Well, is this the one for? Yeah, this is the one for a wide variety of disciplines, right? So this is applying to a whole bunch of things. So it's not just engineering, you know, it's biotech, nursing, radiology, welding, etc. So there's that. And then the David and Mary Lou Chamberlain Scholarship, this is specifically for engineers. And if you just open the attachments, read them all. The Chamberlain Scholarship comes with a description and an application, how to apply. It also comes with a rubric, so how they actually go through and evaluate your scholarship application. I don't know if any of you knew Sydney. She got it last year, and Bryce. Yeah, so that's that announcement. And then there's the announcement of, just to re-announce it here, the 2021 design competition. I didn't get much interest. I got one person who's a first-year student saying they were interested, but they're really in no position to do this by themselves. So if you are interested in the TIESA design competition, this is the one where the design criteria is to design this micro hydro power system to supply AC power to a small household. And you're not going to build this, right? This is not, you're not paying $1,000 here. This is, you're designing this on paper, but the total design or the total construction cost should be less than $1,000. You need to design this thing so it can be designed for less than $1,000. And then it'll be presented at a panel on April 30th. So yeah, I'm still having ENS 219 because no one's signed up. Let's see. Yeah, team registrations next Friday. So I wanted to have an email, or I wanted to set up a meeting this week, but then I didn't get enough interest, so I'm just re-advertising. All right, so I think this is probably a good place to let you have time to do your test, because I mean, I could start the next, oh wait, you know what? We have a few more slides here. Yes, we do. We have a few more slides. I forgot. Summary of capacitors and inductors. I put this in here because I thought it was a nice, this is actually right from your textbook, a nice table. So it just goes through resistor, capacitor, inductor. These are the equations you need. I would just print this out and have it, or you can go to your textbook and know where it is. But these are the relationships, right? The VI relationship, the IV relationship. Again, this is algebra. This is easy. But it's nice to have these sort of, in one spot, because these are not something that you can remember these easily, and you can easily do that, but sometimes you forget the integration constant, or the initial time constant. This is the power for them. This is how they act in series and parallel, and then how they operate in DC, right? DC, same. Capacitor and inductor are short, or open and short. And then, yeah, circuit variable that cannot change abruptly, right? Inductors are pretty bulky. They're less likely to be used in capacitors, or less frequently used in capacitors, but they do have certain applications where they can be used. Oh yeah, I never talked about applications for inductors. So one of the things they might be used for is to create a large amount of current or voltage for a short time period, right? And because they have resistance to sudden changes in current, they can use them for like spark suppression, right? So a place where you might not want the current to spike, or go up rapidly outside of your control. And in combination with capacitors, you can use them for like frequency discrimination. So things like, if you go from one country to another and one's at 60 and 50 hertz, you can use this. So we've covered resistors, we've covered inductors, we've covered capacitors. We will not be covering transistors. That's the conclusion for the slide deck. That's it, yeah. So I will now, well, unless you want me to continue. So the question is, there's a yes/no poll. Do you want time now to go take your test? Would that be convenient? Yeah, okay, that's what I figured. I just want to make sure I'm not ending class and you guys are all disappointed. You're like, oh, I can't believe we're not getting any more exciting lecture. This is just so heartbreaking. All right, so most of you want to go take time to do your test. So let me, oh, I don't know why I did that. Let me stop here then. I'm going to stop recording. Are there any questions